Hello, I'm Raphael Lane, and I'm going to be talking about my video project for a few minutes. At the beginning of the semester, we were asked to pick a simple structure with a clearly identifiable beam element, take a picture, and submit it with some rough dimensions. I picked a sign at Melbourne Central since I walked past it, and it's a very simple structure. Then later in VP2, we were given a basically a formula to calculate a distributed load, and then apply that distributed load to our structure, or just to the beam part of that structure, which we could simplify so that we are just looking at the beam. As you can see here, I've made a fixed end, and now it's just the beam that I'm looking at. It's a linearly distributed load with the maximum given at this point and going to 0. From the distributed load, I calculated a function for that curve, and then using integration, I calculated the shear force and the bending moment functions. Then I applied boundary conditions to determine the points at which these forces are greatest, and also what the magnitudes are at those points. And as you can see, the shear force follows a quadratic curve, and the bending moment follows a cubic curve, which makes sense with integration. And of course, the normal force is 0. From there, I could calculate the deflection of the beam using further integration, but this time incorporating the Young's modulus and the moment of inertia for structural steel. Structural steel being the material that I chose. Although the sign is most likely made out of aluminium, I thought that structural steel would be more interesting for the project. So integrating, I calculated a function for the slope of the deflection as well as the deflection, applying boundary conditions on the way to evaluate the integration constants. Then inputting L representing the length of the beam, I came out with an algebraic expression for the maximum deflection, because, this function takes on its maximum value at point L, and anyway, so we have this algebraic expression. To calculate a numerical answer, I then looked up the Young's modulus for structural steel and calculated the moment of inertia for the cross-section. Then I inputted those values along with the maximum shear force here, and came out to a deflection of 5 millimeters. I drew that and then commented and said that I think in reality there would be a problem with stability. We weren't looking at stability yet, but since it's a thin and deep beam, I imagine it would probably fail due to stability before failing due to anything else, or that it would deflect due to that instead of just the vertical load. Then I went ahead and calculated the shear force and bending moments sort of geometrically, if you will, because we were asked to do it that way, and it was interesting for me to see that the result is the same. Yep. Now on to VP3. For VP3, I made a brief summary of the calculations from VP2, tidied it up a little bit, here's a lovely introduction. Actually, I should introduce. Yes, no, that's fine. Yeah, there's a summary of my calculations from VP2, and then on to VP3. Now for VP3, we were asked to calculate the internal stresses in the beam, and doing this following on from VP2 with the calculations we already had, and applying a few new formulas that we got in the lecture. I've listed here the Young's modulus, the yield strength, and the ultimate tensile strength for the structural steel. Identified the critical points for the normal stress, which is evaluated through this function. Sorry, through this formula, I should say. From there, I was able to calculate the maximum normal force and the maximum shear stress. The shear stress is maximum along the neutral axis. So I used this formula, and I wanted to illustrate the shear as a function of x, and say that the maximum shear as a function of x, I should say, is equivalent to essentially a scalar multiplied by the shear force function of x. And since the shear force is maximum at x equals 0, it's very easy to identify this point here back at the fixed end as being the point that's going to have the maximum shear force. Again, punch in some numbers and come up with the shear force. So this is the maximum shear force in the neutral, in the neutral axis, and up here we have the maximum normal. Sorry, I should have maximum shear stress along the neutral axis, and up here we have the maximum normal stress. And as you can see, the normal stress here does slightly exceed the yield strength. This means that there will be some plastic deformation, but it is not enough to cause a complete failure, since the ultimate tensile strength is 400 MPa. And here the maximum shear is quite a lot smaller than that as well. Then I went on to the stress transformations. I took these formulas. I did have a look at the derivation, but I didn't include them here because it's quite lengthy and probably not necessary. I did derive the rest of the formulas though for the angles and the principal stresses. Once all those formulas were derived, I went on to evaluating them, evaluating the principal stresses and shear stresses, etc. So starting for points A and B, where the normal stresses are greatest, I put in some numbers and calculated that the maximum shear at that point happens at a rotation of 45 degrees, and that it comes out to 127 MPa. I did the same thing for point C, principal shear stresses. Well, the principal shear stress is at theta equals 0. The principal normal stresses came out to be at theta equals 45 degrees, or plus or minus 45 degrees. And then referencing all of this information and having put those theta values back into the functions, I was able to make a guess at the failure planes, and I've drawn them on here. Here's my deflected beam, and here's, as you can see, between A and C, there's really at point A, there's a maximum normal stress, which would cause a vertical fracture, or at least it would cause it to stretch at that point. And I've drawn the other stresses on there as well. And then I drew a couple of more circles, mainly for me to learn a bit more about these, but also I think it's pretty great how simple they make all the information. It's very clear from here what's happening with the principal stresses, then rotating 2 times theta to the 90 degree, which is 45 degrees for theta. You get the tau max and tau min, and the same thing for point C. It's visually very, makes the information much more easy to understand. Anyway, in conclusion, it was an enjoyable task. I learned a lot. I realized that there are some limitations because stability wasn't accounted for, and also the combined shear and normal stresses weren't accounted for. So the reality would probably be a little bit different, but anyway, I think we'll probably be learning more about this soon, and I'm looking forward to it. Thank you for watching. I hope this video didn't end up being ridiculously long, which it probably did. Sorry about that. And thank you.